sans plus tarder, je cède la parole à Dorothy Barthélémy. Dorothy est professeure agrégée à l'École de réadaptation de l'Université de Montréal. Elle est également chercheuse au CRIR et responsable du créneau mobilité ici à l'IURDPM. Alors, bienvenue à cette conférence. Dorothy, à toi la parole.
Bonjour, merci beaucoup, Frédéric. Merci à vous. Merci de vous joindre à nous. Alors, en effet, aujourd'hui, la conférence va être donnée par le professeur Marc Roig. Marc Roig est un chercheur à McGill, professeur associé. Il a quand même une bonne liste en éducation qui est très, très intéressante en ce sens où il a fait un baccalauréat autant en physiothérapie et un autre en kinésiologie. Il a fait une maîtrise en sport science à l'Université de Nottingham en Royaume-Uni. Par la suite, il a fait un doctorat à UBC, donc l'Université de Colombie-Britannique, et un post-doctorat au Danemark, au laboratoire du professeur Jens Bo Nielsen. Donc, vraiment, il a beaucoup d'expertise, autant en exercice qu'en réadaptation. Et il a maintenant son propre laboratoire. Il a été recruté à McGill, le laboratoire, le Memory Lab, qui est situé à l'hôpital juif de réadaptation, et il va nous parler un peu de l'effet de l'exercice sur la récupération post-AVC. Encore une fois, c'est un plaisir de t'accueillir, Marc. À toi la parole.
Thank you. Thank you, Dorothy. I want to thank Dorothy for inviting me and Eric and Vincent for organizing all this so well. Thank you so much. So today I want to talk to you about two projects that we just finalized in my lab. Okay. In my lab, we do different things, but these projects will be about exercise in a stroke. The goal of these two projects, two randomized control trials, is to study the effects of cardiovascular exercise in people with a stroke at different stages of recovery. Okay. And the idea is to see if this intervention can promote brain plasticity and also cardiovascular health. Before I start, I want to thank these people because they did all the work. I didn't do much. So these are two PhD students in my lab, Bernard and Lyndon. They're finishing his PhD and they're just writing their thesis. And this is Kevin, who did part of the project, one of the projects, trial 2 at McMaster University. Kevin is now a postdoc in the lab too. Okay, so thank you so much. I'm just presenting what they found. I didn't do much. This is the way I organize the presentation. These are different points I want to go through. First of all, I just want to give you some background information, just some points about stroke statistics, brain plasticity, cardiovascular exercise, and the different terms that we use to define different stages of recovery post-stroke. And then I want to talk to you about the two trials that I'm going to present. The trial number 1, in which we use cardiovascular exercise in people with subacute stroke. And we train them for 8 weeks, and we compare the training group with an acute care group that we had in the hospital. The outcomes that we're going to focus on are cardiorespiratory fitness and brain plasticity. And you're going to see that we use different biomarkers to measure brain plasticity. And then we're going to move on to randomized control trial 2, in which we're going to also talk about the effects of cardiovascular exercise, but in this case, in people with chronic stroke, not subacute stroke, okay? In this study, we really look at intensity. We wanted to compare high-intensity interval training and moderate intensity cardiovascular training, as you can see here, okay? And we are going to look at 3 outcomes, cardiorespiratory fitness, brain plasticity biomarkers, but also psychosocial responses, motivation and enjoyment. Let me give you some basic statistics about a stroke. Probably some of you already know this. A stroke is a leading cause of disability and is one of the leading causes of death worldwide. We have a stroke every 5 minutes in Canada. And we know that if you survive the stroke, 50% of patients will recover almost fully, but 50% of them will not. So they need treatment. The stroke can produce, can have different manifestations. You can have cognitive problems, you can have psychological problems. But for the sake of this presentation, I want to emphasize that the stroke also has huge effects on cardiorespiratory fitness and physical activity. So we reduce our cardiorespiratory fitness and we become less active when we have a stroke. The way you're going to recover from a stroke depends on many things. Depends on your age, depends on your sex. Many factors can contribute, to see if you recover well after a stroke. But from a mechanistic point of view, the most important factor is brain plasticity. Brain plasticity is defined as the capacity of the brain to repair itself, in this case, in this context, okay? And we know that brain plasticity is essential for brain recovery, and that's why most of our stroke treatments are based on principles of brain plasticity. We also know that there are some windows of opportunity, meaning that we need to implement our strategies, our rehabilitation in some specific periods where the brain is more receptive, okay? We know that. We don't know exactly which window for each outcome, but we know that there are some windows where we can implement our strategies to maximize the effects. So what we try to do is to find treatments that can promote brain plasticity and therefore maximize the capacity to recover in each patient. One of these treatments obviously is exercise. And in this case, we're going to talk about cardiovascular exercise. We have a lot of evidence, especially in neurotypical populations, that cardiovascular exercise can promote changes in brain plasticity. We also know that in animal models, this type of exercise helps animals to recover better. In humans, we don't have the same amount of evidence, so we're still trying to understand if this exercise is really something that can change the brain and how this is going to help recover better in humans. And we also do not know what is the best period to introduce exercise post-stroke, and what happens if we increase intensity, okay? Maybe if we increase intensity, we can maximize, again, the effects of this intervention on recovery. So before I show you the data of our randomized controlled trials, I just want to talk briefly about semantics and how we define the different stages of a stroke recovery. I think this is essential. Stroke is a very particular clinical condition. It's not a neurodegenerative condition. The stroke happens one day and it changes your life. So there is an event. There is a cerebrovascular accident that is going to change your brain, okay? That's important to understand. And after the stroke, you're going to go through different stages of recovery. Here you have some of the stages, and I think it's important to understand that each stage is characterized by specific aspects of the biology of the brain in terms of recovery. For example, the hyperacute stage goes from 0 hours to 24 hours, and it's characterized by an increase in the hematoma in the brain. The acute stage goes from 1 to 7 days, and it's characterized by inflammation. And then 7 days to 6 months, we start what we call the subacute stage. And we divide these into 2 phases. The early subacute that goes up to 3 months, and then the late subacute that goes up to 6 months. Patients after 6 months, we call them chronic stroke patients, okay? I'm just bringing this up because I think it's important for you to understand these stages and make sure that when I say subacute, you understand that this goes from 7 days to 6 months. And when I talk about chronic, we go from 6 months onwards. So the first trial that I'm gonna present is gonna use cardiovascular exercise to try to improve different aspects in early subacute patients. And the reason why we wanted to implement this exercise here is, first of all, because we don't have a lot of data, but also because we know from animal models that these, as you can see in the green line, these stages really reach in terms of brain plasticity potential, okay? The windows of opportunity that I was talking about, this seems to be one of those windows that we need to take advantage of. The second trial, randomized control trial 2, will deal with patients in the chronic stage. And why chronic? Well, what we think is that if we increase the intensity of exercise enough, maybe we can reopen this window of brain plasticity that we had in the early subacute stage. Okay, we don't know that. I hope you follow me. Yes, good. So this is randomized control trial 1. The man in charge is Bernard de las Heras, who's here in the room. Yeah, I think you look older today, probably, because you aged through your PhD. This is the title of the paper that we're going to submit very soon. In this study, we look at cardiovascular exercise and brain plasticity, again in subacute stages. I'm just showing you the flow chart of the study. As you can see, in this study, we really try to recruit people that were in the hospital, inpatients. We, of course, screen for eligibility, and we did a baseline assessment. I'm not going to explain you everything we did because we did many things. If you have questions after, we can discuss. Then we randomized them into two groups. One group was allocated into the exercise intervention, and the other group was allocated into the control intervention. The control intervention, they just receive usual care, okay? And this group here, they receive our intervention. I'm going to explain you the intervention in a minute. They went through 8 weeks of treatment with 2 more assessments at T1, week 4, and T2, week 8. And we did the same for the control group. So this is the intervention that we use. So what we did is we started with moderate intensity cardiovascular training. This is this abbreviation here. And we did 4 weeks of this. So we started very progressively at 65%, 80% of the heart rate max. And we progressively weekly increased this intensity. And we also increased the duration of the training sessions, okay? They were training with us 3 times per week. After 4 weeks, we moved these guys into the HEAT protocol. And we asked them to exercise using this HEAT paradigm, as you can see here, with different bouts of high intensity combined with bouts of lower intensity. I hope you guys know what HEAT is. HEAT stands for high intensity interval training. So instead of just doing one long bout of exercise at a submaximal intensity, HEAT allows you to go super high in intensity because you have periods of recovery in between, okay? So it's important to understand that in this case, they train for 20 to 35 minutes. And in this case, they always train for 20 minutes. So in total, they perform 8 weeks of training. So in this study, we measure a bunch of things. We measure genotype, we measure motor function, we measure motor learning. But today, I just want to focus on these 3 outcomes. So the first one is cardiorespiratory fitness. The second one is brain-derived neurotrophic factor. This is BDNF. This is a protein that we wanted to assess because we believe that it's really behind cognitive processes, recovery after stroke, memory. It's a super important protein that we know that if we inhibit, for example, in animal models, they do not learn, for example, they do not recover well after a stroke. So we wanted to see if exercise can increase the amount of this protein in the blood and see if this was associated with better recovery. We also look at brain plasticity in the brain. In this case, we use corticospinal excitability. We use transcranial magnetic stimulation to measure different measures of corticospinal excitability. I'm going to explain this in a minute. For cardiorespiratory fitness, we use a graded exercise test on our recumbent steppers. If there is any clinician in the room, this is like the typical stress test that you will do with your patients to make sure that they don't have contraindications to exercise. And what we do in this test is we put the patient on the recumbent stepper and we do a warm-up, and then we start increasing the intensity of the protocol every 2 minutes until they cannot continue with the exercise, okay? The way we define cardiorespiratory fitness is by measuring VO2 peak. This is maximal oxygen consumption, defined as the maximal oxygen that they were using when they stopped exercising because they could not continue. We took all the measurements like workload, gases like VO2, CO2, heart rate, blood pressure, but also RPE. RPE is rate of perceived exertion, meaning how fatigued the patients were when they were doing the study, okay? Brain-derived neurotrophic factor, we took blood samples. It's important to say that in this study, we look at the chronic response, meaning that in all the data points that I show you, baseline, T1 and T2, we measure at rest, all these things. but we also measure the response to exercise. So we also measure the acute response of all these outcomes, okay? So in this case, we measure BDNF before exercise, but also after exercise. We extracted serum BDNF, we store the samples, and then we use ELISA to analyze the concentration of these protein in the blood. I'm just going to spend some time explaining you TMS, because if some of you do not know TMS, I think it's important because it's going to be one of the main techniques of this presentation. So TMS stands for transcranial magnetic stimulation. And what we do is we stimulate different areas of the brain using a magnetic coil, a magnetic stimulation that depolarizes neurons in the scalp and in the cortex. And it allows us to measure, again, the excitability, especially of the corticospinal pathway, okay? We put electrodes in the hand, so we know when we stimulate that area of the brain that represents the hand, we can capture the movement of the hand. Think of this like a cable. You put electricity in and there is electricity out. So you put some electricity and then you measure the output. And we also use neuronavigation. So this is a very cool system in which we can put the coil, as you can see the tracking system here. So the coil has a tracking system, so you can put the coil in specific areas of the brain and be very precise and repeat these measurements, you know, in different times during your study. So I'm just going to run a video so you can see how we measure corticospinal excitability. But again, we put the coil in the primary motor cortex, we stimulate, we send pulses, and we collect this information using electromyography. So the video that I'm going to show you, I want you to pay attention to this window here. Just forget about this window. And what you're going to see is you're going to see a stimulus coming at 1 second, and then a response. This guy here is the response you're going to see. We call this motor evoked potential, or MEP, okay? I'm going to run the video. So you cannot hear the noise, but normally you should hear a clicking noise. So again, you see here, we send a pulse at 1 second, and then we get a response. By measuring this response, we get a sense of the excitability of the corticospinal pathway and interconnected structures like the spinal motor neurons. The way we normally measure excitability is by using two approaches, or a combination of these two approaches. One is to measure what we call the resting motor threshold. This is just how much intensity we need to use in the stimulator. It's called the percentage of the maximal stimulation intensity, maximum stimulation output of the TMS machine. So this is like a percentage. It goes from 0 to 100. So more intensity means that you're going to need more intensity to produce a response. But we can also measure the amplitude of this guy, the MEP. So we can measure the amplitude of this guy. The wider this MEP, the more excitability in your corticospinal pathway. Okay. This is more complex than what I'm explaining because we use different methods and different protocols, and we use pair protocols, and we use pair pulse protocols and single pulse protocols. But for now, I think it's more than enough for you to understand what I'm trying to explain. I'm going to try to explain why measuring corticospinal excitability post-stroke is important. Normally, when you have a stroke, let's say that you have a stroke on this hemisphere, we call this ipsilegional site, okay? Normally, what you see is a reduction of the excitability in this hemisphere, and also an inhibition. So the area that has been damaged really shuts down completely, okay? And sometimes what we see is an increase of the excitability of the unaffected side. We call this contralesional side. So this side has not been affected. So we see that excitability goes up, and there is also a facilitation. There is a facilitation to see more excitability, okay? So basically, when you have a stroke, all your hemisphere balance gets disrupted. You have no excitability in the affected area and a lot of excitability and facilitation in the unaffected area. When you have patients with these patterns, no response or a lot of reduction of excitability, a lot of inhibition, and you have a lot of activity in the non-affected area and the control lesional side, this is normally a sign of poor prognosis. Normally, these patients do not recover well, okay? What we aim to do with our therapies is to rebalance this interhemispheric ratio and make sure that there is more excitability in the affected area and less excitability in the control lesional side. Do you understand? It's like just rebalancing the two hemispheres. I just want to say that what I'm explaining is very simplistic, but it's not. It's more complicated than what I'm saying. And we have many, many patients that do not follow this pattern, okay? But just for the sake of simplicity, I just wanted to explain you this and just for you to understand what we expect in terms of good prognosis or bad prognosis when we see these changes in excitability. I'm just showing you now the results of the study. Here you can see the demographics. So as you can see, Bernard recruited a lot of patients. This is the largest randomized controlled trial that has been ever published or will be published, I hope, in subacute stroke looking at brain plasticity. So as you can see, he recruited a lot of participants. We divided them into the exercise and the control group. And as you can see quickly, there are no significant differences in the demographics. So when you look at the age, the sex, the BMI, the stroke location, and other measures such as the level of the severity of the stroke, the cognitive level, the functional, the Fugel-Meyer, and other tests, there were no differences between the two groups, which is good always when you run a randomized controlled trial, obviously. We found, as expected, that the exercise group improved VO2, improved cardiorespiratory fitness quite a lot, okay? So in blue here, you see the exercise group, and in red, you see the control group. So the control group improved a bit because they were receiving usual care, but also because you recover after stroke. These guys are very early in the recovery process. So even if they don't do much, you still can see some recovery, okay? But as you can see, the recovery in the exercise group was massively evident compared to the other group. The line that you see here, this corresponds to 19 milliliters kilogram per minute, which is the way we measure VO2. This is what you as clinicians should achieve if you want your patient to be independent, okay? I'm not talking about spasticity here. I'm not talking about biomechanical problems. That's a completely different story. But if you want your patient to be independent from a cardiorespiratory point of view, you want them to reach, when they leave the hospital, to reach this level of cardiorespiratory fitness, okay? We didn't find anything in terms of brain-derived neurotrophic factor. We were expecting to find anything. We didn't find anything. We didn't find anything in the acute state, in the acute response. We didn't find anything in the chronic. So both groups seem to increase slightly the amount of BDNF in the blood at different time points, but the comparison between the two groups didn't report any kind of significant difference. We have some theories to explain why this happens. The first theory is that we don't believe that BDNF explains the whole story, okay? But we also have other theories, such as, for example, in the subacute stage, you have a lot of inflammation, and maybe inflammation may have an inhibiting effect on BDNF, because there is some evidence of that. When we look at TMS and the corticospinal excitability measurements, we didn't find anything either. Okay, anything significant. So it doesn't seem that exercise changes brain plasticity when we measure it with BDNF in the periphery and when we measure it with TMS stimulating the brain. Here, I'm just showing you an example. Motor evoked potential is one of the biomarkers of excitability that we measure. We were expecting that in the this is only the ipsilesional side, so this is the affected hemisphere. We were expecting that the excitability, the MEP amplitude will go up. And what we found was the opposite. We found that in the exercise group, it went down. So Bernard needed some psychological treatment after these findings, because when you do a PhD and some of your hypotheses do not happen, you feel very, very disappointed. I hope I convinced him that this is high quality work. This is the largest study ever done and reporting negative results is also something we need to do, okay? So the conclusion of this first randomized control trial is, yeah, we can improve cardiorespiratory fitness, but when we use these biomarkers of brain plasticity, BDNF, blood in the periphery, and TMS, corticospinal excitability, we don't see what we were expecting. So this is randomized control trial 2, and this is led by Lyndon Rodriguez, also a PhD in my lab. He's writing his thesis now. And in this case, we were focusing on chronic stroke patients. Okay, so these are patients that had the stroke at least 6 months after entering the study. Okay, and we use transcranial magnetic stimulation. We also measure other things, but I'm just going to focus on the corticospinal, on the TMS measurements, on the CSC measures, on the corticospinal excitability measurements. Another thing that we also wanted to explore with this study is if intensity changes things. Remember when I show you the different windows of plasticity and I told you maybe in the chronic stage, our brain is not receptive to exercise, but maybe if we increase the intensity of exercise, maybe we can reopen this window of brain plasticity. And that's an hypothesis that we put forward in this paper, in which we tried to propose that we could try to use high-intensity interval training after stroke to try to improve VO2, but also improve different aspects of brain plasticity. This is the flow chart of the study. In this case, we were recruiting outpatients mostly, okay? So patients that were not in the hospital anymore. We screened them, and then we did a baseline assessment, and then we randomized them into 2 groups. One group did MICT, moderate intensity cardiovascular training, and the other group did high intensity interval training. And they did all these for 12 weeks. Again, they trained 3 times per week with us, okay? We have one assessment at the end of the interventions, and we have another assessment 8 weeks that follow up, but I'm not presenting this in this study because we didn't report this in this paper. So again, the intervention is very similar to what I presented in the previous study. We started with moderate, we did moderate intensity cardiovascular training. And as you can see here, we started with 40% of the heart rate reserve. So this is moderate intensity. And we progressively increased the intensity of exercise and the duration. So at the end, they were doing 35 minutes, working at 60% of heart rate reserve. This is the gold standard for cardiovascular exercise in the stroke rehab. It's what most clinicians use. Well, that's not true. Most clinicians will not use this intensity, to be honest with you. They will use probably lower intensities, unfortunately. But this is what is recommended by best practices, okay? The HEAT group performed high-intensity interval training, in this case, 24 minutes. And again, we combine bouts of high intensity with bouts of low intensity, 1 minute, working at initially 80% of the heart rate reserve, and finally, in the last weeks, 100% of the heart rate reserve. Okay, these are the demographics of the study. Again, I want to show up a bit. This is the largest study in chronic stroke, randomized control trial, looking at brain plasticity and using exercise, HEAT versus MICT in people with stroke. Okay, 28 patients in the HEAT group, 28 patients in the MICT group. For this study, we did not include people with brainstem lesions or cerebral lesions in the cerebellum, okay? Because for TMS, it's better to stick to cortical and subcortical lesions. Again, as you can see, no major differences in all the demographics in terms of sex, age, time post-stroke, type of a stroke, disability, severity of the stroke, and the other variables that we analyze. So here we found something, okay? We found the opposite of what we were expecting to find, because we were expecting to find major changes in the subacute, because in theory, that's the window of brain plasticity that everybody talks about. What we found in this study is that this type of exercise, cardiovascular exercise, regardless of if it's high intensity or if it's moderate intensity, produces changes in the ipsilegional hemisphere, in the affected hemisphere. And these changes seem to be positive, okay? So here you can see, again, the resting motor threshold. Remember, this is the output of the stimulator. So the more I increase the intensity, the threshold will go up, okay? And what you can see here is that in both interventions, there was a reduction of the resting motor threshold. So the intensity that we required to see the same response was lower, which is good. It's good because we are looking at the affected hemisphere. And remember that the problem with this guy is that it doesn't have enough excitability, okay? We didn't find differences between the HEAT and the MICT. So when we did comparisons between these two groups, we didn't find significant differences. But we did find that exercise improved this, and that when you look at the baseline and the post-treatment in the MICT, there was a significant decline. Okay? So that's good news. When we look at the motor evoked potential, remember this is the amplitude of the guy that I show you in the video. What we found was also changes in the ipsilegional side, nothing in the contralegional side. So remember that here, increasing the amplitude of the MEP means more excitability. Again, what we found is that both interventions increase the MEP amplitude. Okay. What we found here, though, is that HEAT seemed to be a bit better than MICT. But the message is this type of exercise really has an impact on the excitability of the ipsilegional hemisphere. Okay. We also found something we did not expect. Remember that I told you that we measure a bunch of things. We measure inhibition, we measure facilitation. I don't want to explain you the whole protocols because it will take me 1 hour. But we also found that there was a decrease in facilitation in the ipsilegional side, which we were not expecting. We were expecting more facilitation in the affected side, right? We don't know exactly why this happened, but perhaps it's because these guys had a super high level of facilitation already. And what exercise does is it rebalances this facilitation. It brings the facilitation down, so it's closer to the equilibrium that you need to have homeostasis in your brain, okay? And this is consistent with these data that I'm showing you here. What I show you so far is excitability in the ipsilegional side and the contralegional side. What I'm showing you in this graph is the same measurements, so resting motor threshold, but here I'm measuring the ratio. So I'm measuring the difference between one hemisphere and the other hemisphere, okay? Remember that one of the goals is to try to rebalance this. And that's exactly what we see with this type of training. What we see here is that both interventions, when you analyze the data together, you see that there is a reduction in the threshold, which is a good thing. You need less power in the stimulator to get a good response. And there is a good balance between hemispheres. Remember that the balance is 1. You don't see here, but I had a gray area here. But everything that brings these down to 1 is a good thing. It makes your brain more balanced in terms of excitability. In terms of the motor evoked potential, we also found positive responses. Again, these goes beyond 1, but because you need to increase excitability, okay, in the affected hemisphere, this is potentially a positive change. And again, we found that regardless of the type of intensity that you were using, both interventions improve excitability by increasing the amplitude of the motor evoked potential, okay? Remember what I told you about facilitation. We believe that the reason why exercise lowered facilitation, which is something that we did not expect, is because exercise brings down facilitation, so it makes your brain more balanced, more close to 1, which is the perfect ratio between the 2 hemispheres. This is just an hypothesis, okay? So I hope you follow me. I know this is quite intense, and there is a lot of mechanisms here. It's gonna get easier now, I promise, okay? This is the part of the randomized control trial that was conducted by Kevin. And here we were looking at VO2, okay? We believe that high-intensity interval training can be a good alternative to moderate-intensity cardiovascular training. But we didn't have enough evidence in a stroke. And that's what we wanted to see here. This is exactly the same project that I just showed you, okay? But in this case, I'm just adding a second assessment, a follow-up. So when they finished the 12 weeks of training, they went home, and then we asked them to come back 8 weeks after, and we did a follow-up of all these measurements. The same interventions that I just explained, exactly the same, okay? 12 weeks of moderate intensity cardiovascular training, 12 weeks of high intensity interval training. These are the demographics. As you can see, again, the largest randomized controlled trial comparing MICT and high intensity interval training, 42 patients in the HEAT and 40 patients in the MICT. It takes a lot of time to train 12 weeks, 82 patients. I hope you understand this in the context of COVID, because I think the students should be commended for this, because it's a lot of work, okay? Again, no significant differences in all demographics in terms of age, sex, BMI, all these kind of measurements, no significant differences between the two groups. And this is what we found. What we found is that both interventions improve VO2, but HEAT was better than MICT, okay? It was significantly better. That's the difference between the two groups, 1.8 milliliters kilogram per minute. And this is clinically relevant. Remember one thing, these guys here train for 24 minutes, while these guys trained for 35 minutes. So the time commitment and the volume of training is completely different. So that makes high-intensity interval training a highly time efficient alternative to moderate intensity cardiovascular training. Clinicians will say, I don't care, it's just 5 minutes more. Well, it's almost 10 minutes more. It's 20% more time and more volume, and you get better results. So I think we can implement this. We didn't have, by the way, we didn't have any adverse event related to the intervention. This is in line with a paper that Kevin published very recently in the British Journal of Sports Medicine. This is a meta-analysis in which we look at different interventions. So high intensity interval training, this is high intensity cardiovascular training, this is moderate intensity cardiovascular training, this is low, and this is no exercise. And the line that you see here, this is what marks the difference between usual care, okay? And as you can see, HEAT in this network meta-analysis, when you take the data from all these trials, is the best intervention to improve cardiorespiratory fitness. So intensity really matters if you want to improve cardiorespiratory fitness. Improving cardiorespiratory fitness is absolutely essential, okay? It's related to mortality, it's related to quality of life, it's related to the risk of having a stroke. The question now is, okay, this works, but will patients do it? Because maybe this is so intense that, yeah, you can do it in a randomized controlled trial when they have the student in front of them, they have like a personal trainer pushing. Can they do it really? Well, in this study, Lyndon looked at the psychosocial responses of exercise. So he looked at 3 things: enjoyment in response to HEAT or MICT, motivation, and also the effect while doing the training. I'm going to explain this in a minute. Again, this is the same project. Okay, it's the same project, but as you can see here, the time points of the assessment are a bit different. Week 1, week 6, week 12, and the same here. Okay, and the reason why they are different is because depending on the tool that you use, you need to vary a bit the timing of the assessment. As I was saying, we look at 3 things. First, the effective response that we evaluated with the feeling scale during training. So we were asking patients, hey, how do you feel now? And we asked them in the beginning of the session, in the middle of the session, and then at the end of the session, okay? We also use the physical activity enjoyment scale to measure enjoyment. So did you enjoy what you did? All these kind of questions, we use questionnaires. And we also use the BREC-3, which is the behavioral regulation and exercise questionnaire to measure motivation. Okay. So again, as you can see, the numbers are a bit different here because not everybody completed these questionnaires, but as you can see, the numbers are pretty nice. 37 participants in the HEAT group and 34 in the MICT. Again, no differences in terms of demographics, as you can see here. And what we found is this. When we look at the effective response, when we're asking them with the feeling scale, hey, how do you feel about what you're doing right now? What we found is that in the HEAT group, there was a decline. And this decline was significant. So for clinicians, the message is, hey, you need to be with the patient when you start doing HEAT with them. You need to inform them. You need to warn them that maybe in the beginning, the effective response won't be the same because it's tough, okay? But it's important to inform them so they don't quit. Because when you look at enjoyment at the end of the session, the level of enjoyment was identical. It was very similar between the two interventions. So both MICT and HEAT seem to trigger the same levels of enjoyment. When we look at motivation, I know this table is a bit complex because motivation can be stratified in different concepts. But basically, the most important column is this one. As you can see, no differences in motivation when we compare the different domains of motivation in HEAT versus MICT. Okay. So the message here is, it seems that HEAT is as implementable as MICT. The only thing you need to be careful about is that in the beginning of the sessions, especially, when you start implementing HEAT, you need to be with the patient and make sure that they understand that the effective response perhaps is a bit more negative than when we start MICT, which makes total sense. I'm just finishing my presentation here. These are the home messages. In the first trial, what I show you is that in supraacute stroke, cardiovascular exercise improved cardiorespiratory fitness, VO2P, but seems to have little effects on brain plasticity that we measure via BDNF and corticospinal excitability. In chronic stroke, I show you in the second trial that regardless of the intensity that you use, cardiovascular exercise seems to have effects on the ipsilegional side. It seems to have positive effects on the ipsilegional side. And it seems to have a rebalancing effect, making the brain more balanced in terms of excitability, which we believe is a good thing. Okay. What we also found with Kevin's study is that HEAT is better than MICT at improving VO2. It's not only better, but it's also more time efficient because you get more training less time. Okay. And finally, what we found in the last study, in which we look at the psychosocial outcomes, is that HEAT triggers some lower effective responses during exercise. So people may feel in the beginning that it's not what you're asking me to do. But in terms of enjoyment and motivation, no differences between high intensity interval training and moderate intensity cardiovascular training. I just want to thank my lab, all the members of my lab. I also need to thank these guys for giving me money to do this. I also want to thank Ada Tang because she was a collaborator of the study. Remember that the second trial happened in my lab, but also at McMaster University. Thank you so much.
So I think we will go with the regular questions. I don't know if there's some questions in the room or in the.
I have a basic question for Marc. The cohort of 82 people, were they recruited entirely at Jewish rehab, so where your lab is at, or across several CRIR sites, or even outside of CRIR?
We use all the potential sources. We use you. We use other CRIR sites. We recruited from the community, Fazil Abal, and also McMaster, because McMaster, they also recruited people. So yeah, we try to recruit as many people as possible from as many sources as possible. Yeah. Thank you.
Sinon, pendant que vous pensez aux questions, j'avais peut-être deux petites questions. Ah, merci, je pensais que c'était... OK, j'avais peut-être deux petites questions. La première, ben, en fait, je suis intéressée par, ou un peu intriguée, I'm a bit intrigued by the differences that you saw between subacute and chronic. You saw with similar protocols, changes in chronic, which you didn't see in subacute. Maybe what's the explanation for that, you think? Do you think that maybe in subacute there's already a change in the biochemical environment, and so it's really optimized, whereas afterwards you're not into this window that you explained at the beginning, and so you are getting back to that? What is your thoughts on this?
Yeah, that's an excellent question. So what we think happens, so when you plot all the, for example, if we look at the CSC data, the corticospinal excitability, and you plot the chronic study versus the subacute study, the variability in the subacute is way bigger. So the variance is insane, okay? So what we think in terms of corticospinal excitability is that in the subacute brain, a lot of processes, inflammation, a lot of things are still happening. So it's not that it doesn't work, it's that you have so much inter-individual response differences that probably you need a huge sample size to see the effect that you are seeking, okay? One thing that I did not explain is that we also look at genotypes. So we're analyzing genes and we're trying to understand why some people responded more than others. And that's part of the subacute study that Bernard is writing. So we're going to build a polygenic score to see if we can understand perhaps why we don't see what we see, what we were expecting to see, okay? That's one possibility. In terms of BDNF, there is quite a lot of evidence that when you have a stroke, you have a lot of inflammation, residual inflammation, chronic inflammation. And animal studies show very clearly that inflammation can inhibit BDNF, for example. Okay. The graph of BDNF is puzzling because it seems that all of them, the two groups kind of recover, correct? The BDNF levels, meaning that perhaps we don't see differences because when you recover, BDNF goes up regardless of your intervention. But we didn't see any summative effect of BDNF in the exercise group. So a lot of things are moving in the subacute. That's our hypothesis. And this is something that it does not apply only in this study. It applies in many other studies. If you want to do subacute studies, you need to double the sample size sometimes because the variability is going to be much more compared to the chronic.
Okay, thanks for that. I don't know if there's questions. Yes, Cyril. Wait, I'm just going to bring the... so this is, we just say your name before. Thank you.
Thank you, Cyril Duclos, researcher here. Thank you, Marc, for the presentation. This was really nice. Your trainings are based on intensity, but between your subacute and your chronic, their motor capacity probably improved. So you control the cardiorespiratory effort, but what about the number of movements they are doing? Because when we speak about intensity, it's not clear what is important. Number of repetitions, steps, duration, whatever you do, it's not clear what's important. Is it possible that the difference in plasticity is due to the amount of movement they were doing rather than another factor? No, even during the study, because when they are cycling, they may not be cycling at the same speed.
We collected all this data. So Bernard, we have a lot of training data, heart rate, workload, steps, cadence. We also, because the exercise group also received visual care. So I asked Bernard, we need to monitor what they do upstairs. And there are no differences in number of sessions, type of sessions. So it seems that the groups were doing pretty much the same, except for the exercise group that had the exercise intensity, the exercise protocol. So we didn't find any correlation between all these changes, all these deltas in movement or number of sessions, intensity, heart rate. We explored all this. We didn't find any correlation that could explain the no difference between groups. We use linear mixed methods for the analysis, and we use covariates like MVC, for example. We also use, we use different covariates to try to control for factors that could affect. But again, we didn't see any significant difference between groups.
And you compare the subacute and the chronic? because that's because you see difference in plasticity, mostly in the chronic group, where they might be more able to move. That's more my point.
One analysis that it's pending is to try to understand how different parameters of training, again, intensity, heart rate, or even calories, all these kind of things, could affect the response in terms of brain plasticity or in terms of cardiorespiratory fitness. And we want to combine the two groups. One thing though, remember that the second trial, they exercised for 12 weeks. And the other guys exercised for 8 weeks just because they were leaving the hospital and we cannot retain them. But that's a pending analysis that we want to do, because maybe we find, a parameter of training that will explain why, some patients. Also, the genes will hopefully tell us something. Maybe we find that in the control group, we had people with super genes and they recover. And in the exercise group, we had people with poor genes and they did not get the response that we were expecting. Yeah.
Thank you.
So Marc, there are two questions coming from the chat window. The first one goes, all the studies shown have a NIHSS score of minor stroke severity. I find it hard to get the heart rate up to your 85% with more severe stroke patients that have bigger motor control incapacities. Do you expect that the more severe stroke patients could have similar gains with cardiovascular training?
That's an excellent question. That's a problem in all stroke studies, I will say, because it's more difficult to recruit. We tend to recruit people with low levels of disability in general. I really think that high-intensity interval training is applicable to people with very low levels of fitness and a lot of disability. In fact, we're trying now with the spinal cord injury. It's challenging, it's very challenging, but I do think that it has a space as long as you adjust the intensity for the disability level of the patient. And that's something that we can explore in the future for sure. Yeah.
Thank you. There was a second question for someone named Sophie Ouimet. You have mentioned in your presentation a VO2 of 19 is considered independent, but what activities do you mean by independent? And why is the value 19? Where does this particular value come from?
Tell Sophie to email me and I'm going to send her the paper by Michelle Ploufman, where she estimates that 19, this is adjusted to stroke, it's 6.5 MET. They estimated that this is the threshold where you have to go for. And I really like that threshold because it gives clinician a goal, okay? But tell Sophie to email me and I'm going to send her Michelle's paper so she can see how they estimated these 6.5 MET or 19 milliliters kilogram per minute as a threshold to become independent. They have a nice graph where you can see the patient sitting and then taking a shower and then still climbing, and you can see what is the threshold. Okay?
Oui. Nous mettrons une adresse dans la fenêtre de clavardage. Il y avait des questions dans la salle.
Thank you, Marc. Fantastic presentation. And going to compare to upper limb results. So one of the recent paper by Alex Romerick is called the CPAS study. And they look at the timing in the subacute stroke. And they found out that actually waiting to deliver, in addition to regular therapy, to deliver extra therapy seemed to be more beneficial. Proof of concept, they're not there yet, but yeah, within the first 6 months. Anyone in the chronic didn't change for the upper limb. If you were doing another RCT, would you consider like testing maybe the first month post-stroke versus delayed intervention?
With Bernard, we've discussed this many times. I'm a bit critical with the windows of plasticity theory. I do think they exist. I mean, if you look at animal research, it's clear that, if you start too early, too intense, or if you look at the AVERT study, for example, which is not exactly the same, but too early, too intense is not a good thing. If you wait too long, it's not a good thing. My feeling is that depending on the outcome, this window shifts though. So we have evidence, for example, that if you start doing cardiovascular exercise from 0 to 3 months, if you look at the long run, you're going to see more improvements in mobility, gait, all these things. In VO2, it doesn't seem to be the case. It seems that you can improve VO2 and maintain VO2 even if you start 3 months after. That's reported by Marzolini in a beautiful review. So I don't know what I will do. I think there is a timing. You have to think, though, that these projects are really difficult because how do you convince people not to exercise until month 3? It's tough to do this kind of studies. And my feeling is that every outcome will have a slightly different window of plasticity. Yeah.
On a 2 autres questions en ligne. The first question from Elena Sedesova. This may be a far-reaching discussion, but could this mean that offering follow-up rehab in the chronic stage may be even more beneficial for some patients?
I think we have to be careful not to compare the 2 studies, okay? I think that exercise has benefits. By the way, the fact that we didn't see anything in corticospinal excitability or BDNF doesn't mean I'm saying don't do exercise these patients, because there are so many benefits, like the prevention of having another stroke, which is the recurrence rate is very high. So I think we have to be careful when we compare subacute and chronic. I don't think it's more beneficial to do exercise in chronic than in subacute. I think it depends on the outcome. I think perhaps the biomarkers that we're using for brain plasticity are not sensitive enough to capture change in the subacute stage. But I wouldn't say that, of course, if we could train chronic patients, that would be fantastic. They will improve, and they improve a bunch of things. But I wouldn't say that I will wait, don't touch the subacute for exercise, and then I will wait until the chronic stage. I will never do that, because there are so many benefits that we have not discussed, like blood pressure, a bunch of risk factors that can predispose people to have another stroke, for example. And exercise is so effective in reducing all these risk factors that I will implement exercise as soon as possible. Yeah.
Thank you, Marc. It is now 1 p.m. So for the benefit of those amongst our audience that need to go back to work or their duties, je vais simplement dire merci beaucoup d'avoir participé à cette présentation, d'avoir assisté à la conférence du professeur Marc Roig. La présentation d'aujourd'hui, je tiens à rappeler, a été enregistrée. Elle sera mise à disposition des personnes qui l'auraient manqué sur le site web iurdpm.ca. Nous vous invitons aussi à porter attention à votre boîte de réception. Un courriel avec un questionnaire d'appréciation vous sera prochainement acheminé. Nous vous invitons à y répondre parce qu'on essaie toujours de s'améliorer. Nous vous invitons à vous abonner à l'infolettre de l'IURDPM. Et puis, pour celles et ceux qui peuvent continuer les échanges, si Marc est disponible, il y a une autre question dans la fenêtre de clavardage ou 2, non? Oui. Et on peut continuer à échanger ici. Donc, merci à tout le monde d'avoir assisté. The other question online, and we can come back here. Why do you work at 60 to 85% at the subacute stage, yet I'm missing the second part. Yet at the chronic stage, you use a lower percentage? Apologies.
That's not entirely true. So, of course, in the subacute, I reported the intensity using the heart rate max. In the chronic, I reported intensity using the heart rate reserve. So these are 2 different ways to measure intensity. In fact, Bernard reports the intensity using PPO, not heart rate max, okay, which is power output. So they're not comparable. They are different ways to measure intensity using the heart rate. Yeah.
Est-ce que des questions dans la salle? C'est bon. Alors, merci à tout le monde. C'est ce qui conclut notre présentation d'aujourd'hui. Merci d'avoir été présent. À une prochaine.
Thank you.